So you can talk about the same thing, probability. What's the probability that the what's the probability that the number of households having two or more children, all right, given that the households are senior households. That means given that both parents are 50 and above. Okay, so it's clearly defined. And then you have to start having a new denominator, right? And you have to find those households that begin, first of all, with both parents are 50 and above. And then you kind of look at how many children do they have. Two or more? Okay, one. Another one? No, one only. Another one, no, they don't have children? Fine. Another one, three children. Okay, so two counts, and so on. So that is basically counting what is already defined in B. In addition, also satisfies the A criteria. You see that? So there are many cases when we want to talk about conditional probability. So that's very useful. But my caution, my warning to you is don't get too engrossed with the word conditional. I totally don't like this name, but it's stuck there, right? So I'm not going to excuse you from that. But it's very important not to use the English sense of the word conditional to think too much about it. The way I pick it up is to basically understand that as a changed denominator. Okay. Another very important observation I have to share with you is this. P of A given B, right? And we learned earlier on that probabilities are always about the future, about the unknown. Here is a little bit of a twist, right? So P of A given B, two events, we know that. The A here is the interested event, and that is the a well-defined set. And that event is to be sort of, the probability of that event is to be sought out in future or in the unknown area. But B is a fact that has occurred or is known. So there's no probability about B. You need to understand that very, very clearly here, right? Otherwise, further confusion may happen. So we say probability of A given B. And this given B should be also understood as given that B has occurred, or given that B is known, or better still, reinforce your understanding of B, given that B is known as a fact. Okay, so there's no uncertainty, no probability about whether B occurs or not. B is a fact. It has occurred. It has been known. There is no probability about, no doubt about whether it will occur or not. But A, yes. Okay, A, yes. So that is the kind of situation we want to be familiar with. Okay. So, for instance, what's the probability of a person getting COVID-19 positive? Okay, you can collect from, national statistics and then divide, right? So you can say, okay, the chance of getting Omicron virus, very infectious, 80%. If you happen to be around a person for 30 minutes or more within 1 meter or less, that kind of very quantitative definition, right? To talk about how close you are close, how near you are near. All right. So the probability of person getting COVID-19 positive, right? So let's say COVID-19 positive, that's A. What's the probability of A happening? 80%. Yeah, okay. However, B has occurred. Why? Because your roommate, so two of you stay in the same room, right? Your roommate or your brother, your sister, your sibling, right? Your roommate has been found to be COVID-19 positive. Got it? It is known, it is undeniable, it's a fact. So what's the probability of a person, you, getting COVID-19 positive, given that you have been close to, near to another COVID-19 person, positive person? Well, that changes the whole rule, right? You're not going to say it's going to be same as the national statistics. It's going to be 80%. You might going to say something like, oh, no, I think for sure I'm going to get it, right? You're going to say something like, I think it's 95%. No, I think it's 99%. It's going to change your outlook, even though you haven't tested because you nervously want to just make your own projection before you do the test, right? The test kit test. You make your own projection. What's the chance I'm going to get it? Oh no, let me check it out, right? Or your own reaction is telling you that you have already calculated the conditional probability. Your own rush. Let me quickly test it out. Let me check. Your own rush to do that is already showing that, knowing that you are close to someone who is positive, what's the chance that you are also positive, right? That is a totally different idea, right? It has shot up, right? It has gone up. Yeah. So that's to illustrate why P of A is different from P of A given something. But it depends on what you give, right? What you give, right? Now, for example, what's P of A? What's the probability of COVID-19 person getting in COVID-19 positive? 80%, right? Given that your sibling has just gone to toilet. Oh, well, you know, so we probably don't need scientists to tell us that whether a person that you live close by or will live with has gone to toilet or not will make you higher or lower chance in getting COVID-19 positive, right? So you might just straight away brush it off and say, well, P of A given B is like P of A. You tell me it's like not telling me. Is there any relationship at all, going to toilet and me getting COVID-19 positive more likely or less likely? No, no chance. Don't have to be a scientist to say that. So it depends on what is the given event. Then P of A may be higher or lower than P of A given that B event. Yeah? So just give you some ideas to think about what this vertical bar means, right? So when it comes to calculations, definitely think about the counting. It helps a lot. I can't tell you more than that. Now, why does the counting work? Because when you do the counting, and if I divide by C of U upstairs and downstairs, you see that upstairs is itself a nice definition of probability. So I can say this is P of A intersect B. And downstairs is just P of B, right? So in some textbooks, you will see the right-hand side here equating with the left-hand side here completely without counting. And I don't think that is better or not necessarily worse. It is, shorter. But if you are a first-time learner, I strongly encourage you to go through this thinking about counting process. And then when you do this division, because it's quite easy to understand, and then we fall back on definition again, every step is very logical. And I hope you can be very firmly convinced that this is correct. Yeah. When I started learning, again, the textbooks were giving me P of A given B equals to P of A intersect B divided by P of B. That's the definition. Don't argue with me, right? Well, fine, I memorize it. But look, this is a probability divided by a probability. How do you understand this? It's just tough, right? Is there any way to understand a probability divided by a probability? And I always constantly worry, what happens if this is 0.1 and this is 0.0001? And you will have something larger than 1, isn't it? Is there any guarantee that this ratio of probabilities will not burst beyond 1? And I always kind of like, I can't figure it out, but never mind, that's the definition, and the textbook tells me don't argue with it, right? Well, here is the answer. And because we count anything in A that must have also been in B, the intersection ensures that you will never be larger than B. All right, the lowest you get is A doesn't intersect with B, so 0. The largest you get is A is equal to B, completely is B. So that's 100%. So you will never exceed 1 still. So it is nice to get a lot of insights from the counting process, yeah, than just to chew this formula up and trust in faith that don't worry, right? The formulas won't burst beyond 1. Yeah. Okay, so I hope you can internalize that. Now, just another example is to just flip it over, right? And it helps because now we see that B intersect A intersect B. Hey, actually that's the same thing, right? Because you can flip it and it's the same set. So it does mean that P of B intersect A and P of A intersect B, they are the same number. which means that if you bring up the denominator, so P of A in a given B times P of B, you just times to the left, and likewise for the bottom, P of B given A times P of A. Yeah, you just again bring the denominator to the left. Then what happens is that the P of A intersect B is the same as P of B intersect A. And then we arrive at this very interesting situation. We put them together, and P of A given B times P of B is the same as P of B given A times P of A. That's it. Okay. Now, very, very importantly, all right, this is a definition. And because this is also by definition, and as a result, this equation is also by definition, they work regardless of how A and B are defined. Well, worst you get is 0, right? And another way, and another extreme is you get 1. That's it. But they are still well defined. They are always going to work. They will always work. Why am I stressing this so hard? Because later on, we'll have examples like independence, mutual exclusivity, right? And all these are going to add additional considerations. Can I apply this formula? Can I not apply, right? So all these are like what I call golden formulas. They apply to all circumstances. Probability is definition, and these are definitions for conditional probabilities. They work across all kinds of situations, whether A and B are independent or not, mutually exclusive or not, whatever it is. So it is golden formula, right? So they are very important and very useful because they work irregardless of how A and B are defined. So keep that in mind.